Okay, let's talk about some of the properties or characteristics of the rocks that make up gas and oil reservoirs. In particular, we'll introduce the fundamental concept of porosity. All rocks are porous to some extent, but not all rocks have sufficient porosity to be gas and oil reservoirs. The images shown here are typical of sandstone and limestone reservoirs. We'll talk about these in more detail later. Let's consider the two properties that rocks must have in order to be a petroleum reservoir. Firstly, reservoir rocks must have storage space, that is, there must be openings in the rock called pores. Secondly, these openings must be connected together. The pores are connected to enable the fluids to move or flow within the rock. A scanning electron micrograph of a pore and the narrow connections between the pores, called pore throats, is shown in the image. Note the angularity of the grains and the sharp corners and crevices between the grains and along the pore throats. In the following, we'll use spherical grains, or almost spherical grains, to illustrate the important aspects of pore space and porosity. It's important to remember, however, that except in rare circumstances, most grains are distinctly not spherical. We can get an idea about how the openings in rock are connected if we take a thin section of the rock and magnify it, shown in the images here. We can see the individual grains that make up the rock and the spaces between the grains. The storage space is called porosity. The porosity of the rock is that part of the mass of rock, the rock matrix, that is not filled with grains. The pore space can be filled with gas, oil, or water. Now, the amount of storage space in the rock depends upon four things. The kind of rock, for example, sandstone, dolomite, chalk. The size and shape of the grains that make up the rock. How tightly the grains of the rock are packed together, and any cement, clay, or mineralization filling the space between the grains, such as silica, quartz, calcium carbonate, calcite, gypsum and hydrite, and iron oxides. First, let us consider the way the grains of rock are packed together. Suppose you put some balls, all of the same size, into a container. We find that there are two ways the balls could be packed. At left, the balls are arranged so that each ball is touched on its side by four others. In 3D, this shows a vertical section through a cubic lattice packing. On the right, the balls are arranged so that each ball is touched by six others. In 3D, this shows a vertical section through a rhombohedral packing. In this arrangement, where each ball is touched on its side by four others, there is little more than half, about 52%, of the space taken up by grains. A little less than half, about 48%, is open space. On the other hand, in the lower arrangement, where each ball is touched on its side by six others, about 3/4 or 74% of the space is taken up by grains. Only about 1/4 or 26% is open space. This change in arrangement, or packing, has almost halved the amount of storage space, or porosity, available to hold gas, oil, or water. Here we have the same packings as before, but notice that the balls, the grains, are much smaller. And nevertheless, you can see that, as at the left, where each ball is touched by 4 others, there's still 48% open space. At right, where each ball is touched by 6 others, there's still only 26% open space. What we're saying is that the size of the balls, or grains, makes no difference in the total amount of pore space. The amount of pore space is controlled only by the packing, and not by the size of the grains. Flowing water sorts rocks. When the water is flowing fast, it carries all sizes of rock fragments. But when it slows, there is insufficient energy to move the heavier fragments, so they drop to the river bed or ocean floor. As the water velocity continues to decrease away from the water source, its energy decreases and more rocks and grains are deposited. The smallest material, such as clays and mud, is deposited last. The change in energy of the water sorts the rock grains based on their size and density. This process occurs both in rivers, in estuaries, in deltas, and along shorelines due to wave action. Understanding the basics of different depositional environments is a major component of building effective reservoir models. Of course, real reservoirs are made up of all sizes and shapes of rock fragments and grains. A visual reference for descriptions of sorting and roundness of sediments and grains in classic sedimentary rocks is shown here. Note that rounded grains are not necessarily spherical in shape. Grain shapes are controlled by both the extent of transportation and abrasion, and by the physical properties of the grain. Here's an image of a poorly sorted rock, a coloured thin section micrograph, where the blue is impregnated resin, which fills the pore space. The grains are not coloured. You can see the wide mixture of sizes, from very small up to quite large. The open spaces between the large grains can be filled up with smaller and smaller grains of rock. In the limit, all of the open space would be filled, and the rock would have zero porosity. In the case shown here, there is significant porosity, but a lot less than that of uniform packing with spherical grains. Moreover, it is not clear from the image that the pore space is well connected. However, this is a 2D section, and connectedness in 3D may be higher. Schematically, the lower images show the porosity contrast between well-sorted and poorly sorted grains. Porosity decreases as sorting becomes poorer. Further, porosity decreases as grain sphericity shape decreases, and, also, as grain angularity roundness decreases. The sorting of grains in sandstone plays an important role in determining reservoir quality. The distribution of grain size, for example, grain diameter, is log normal, as shown in the image. The lower image shows a series of log normal distributions, all with the same mean or average grain size, but significant variation in dispersion or spread of grain sizes. One of the most common statistical measures of dispersion is the Truss Coefficient, the square root of the ratio of the 75th percentile, where 75% of the grains have size less than this value, and the 25th percentile, where 25% of the grains have size less than this value. In the lower image, the Truss coefficients range from 1.14 to 3.85. As the Truss coefficient decreases, then the dispersion of the distribution also decreases, and the grains are increasingly well sorted, as shown in the table. A reservoir rock can also have cementing material between the grains. The cement results from precipitation of minerals and clay. The precipitation may leave anhydrite, calcite, silica or iron oxides in the pore spaces. These precipitates cement the grains together. Cement reduces storage space, hence porosity. In some cases, all the space is occupied by cement, resulting in zero porosity. Pore space can also be filled with clay. For example, coarsely crystalline clays, such as kaolinite, may fill up pore spaces, whereas fine fibrous clays, such as illite, can grow between the pores, greatly reducing pore connectivity. As sediment is buried, the grains settle and become more closely packed as the sediments begin to compact. The reduction in porosity by mechanical compaction continues during sediment burial. Water is expelled as the porosity or storage space decreases. At this time, precipitation of cements by chemical diagenesis, such as quartz overgrowths and clay crystallization, may further reduce porosity. Porosity can also be enhanced during burial diagenesis. The primary mechanism for formation of secondary porosity is the dissolution or partial dissolution of framework grains like feldspar and carbonate bioclasts. Many of these secondary pores are larger than the associated intergranular pore spaces. Likewise, carbonate and clay cements may be prone to dissolution, resulting in enhanced post-depositional porosity. Burial depths and temperatures, where formation of secondary porosity is encountered, commonly coincide with chemical reactions involving the breakdown of organic matter. Byproducts of these reactions include carbon dioxide and carbonic acid, and organic acids like acetic acid. There is a fundamental shift in pH and chemical equilibria, particularly for carbonates, and this promotes dissolution. Sandstone porosity can be classified into several types. Primary porosity. This is intergranular porosity that was formed during sedimentation. Primary porosity depends on several factors, such as depositional environment, grain size and shape, distribution of sand grains, and cementation between grains. Secondary porosity. This is dissolution porosity formed during rock diagenesis. Chemical reaction dissolves rock grains and it results in void spaces in the rock. Fracture porosity. This is the void space associated with natural fractures, which can be enlarged due to solution channeling. Microporosity. This is comprised of very small pores between detrital and orthogenic clay materials. Porosity in carbonate rocks can be divided into two major groups, interparticle and vug porosity. Interparticle porosity generally occurs in those carbonate sediments without mud and is divided into intercrystalline porosity and intergranular porosity. Vug porosity can be generally classified into connected vug porosity, which form connected networks such as breccia and fractures, and isolated vug porosity, which can include moldic porosity, arising from dissolution of individual constituents of particles, and intraparticle porosity, arising from voids within particles. Some oil and gas reservoirs are found in rock formations where the porosity is predominantly formed by chemical dissolution of the rock matrix. The top image shows part of the quartz section of Cambrian dolostone, known as the Knox dolomite. The Knox is over 300 metres thick. The porosity system is a complex of matrix porosity, vugs, fractures, and solution-enhanced fractures, seen in the lower image. Dolostone is a crystalline textured chemical sedimentary rock, dominated by the mineral dolomite, calcium magnesium carbonate. Dolomitization is a geological process by which the carbonate mineral dolomite is formed when magnesium ions replace calcium ions in the carbonate mineral calcite. Dolomitization has the potential for creating reservoir quality porosity and permeability in originally tight limestones due to the reduced volume of dolomite crystals. Sandstone porosity is influenced by many parameters, including formation age, mineralogy, maximum depth of burial, sorting, grain size, sphericity, grain orientation, temperature, abnormal pore pressure, hydrocarbon saturation, and formation water chemistry. Of these, depth, age, sorting, and detrital quartz content, as a percentage of solid rock volume, are the most important. Shearer derived a regressed equation for sandstone porosity from these parameters, with a standard error of 2.1%. The equation is valid for sandstone with cement less than 2.1% bulk volume, no leaching, that is, no secondary porosity, depth of burial more than 500 metres, and older than 3 million years. If quartz content and sorting are unknown, representative values of 75% quartz and a Truss Coefficient of 1.5, corresponding to a moderately sorted sandstone. The chart shows the variation in porosity for representative values: quartz 75%, age 5 million years, depth 2.5 kilometres, sorting 1.5. As a rule of thumb, a fairly well-sorted sandstone will have a porosity of between 15% and 25%, and over 30% in unconsolidated and fluvial systems. In limestone, as shown below, the porosity will be between 5% and 18%. If there is secondary porosity present in the limestone, for example, solution or diagenetic porosity, then limestone porosity may exceed 30%. Typical ranges of porosity seen in gas and oil reservoirs are given in the table. Even though most limestone reservoirs have porosity less than sandstone reservoirs, they are often very thick and may be fractured, leading to high production rates. Grain volume can be measured using Boyle's law. A reference cell of known volume, at known pressure, is filled with helium. The sample, whose grain volume is to be determined, is placed into an evacuated chamber of known volume, which is connected to the reference cell by a valve. The valve is opened, and the helium expands and fills both chambers. The equilibrium pressure of the system is monitored, and Boyle's law is used to calculate the grain volume. The bulk volume of the sample can be calculated using Archimedes' principle. The saturated sample is weighed in air and re-weighed while immersed in mercury. The difference in measured weights divided by the density of mercury gives the bulk volume. The pore volume is the difference between the bulk volume and the grain volume. Okay, we've just had a brief introduction to porosity, the storage capacity of reservoir rocks. There's a lot more to discuss about porosity, its relationship to permeability, capillary pressure, and relative permeability. All of these topics are discussed in more detail later, once we've been introduced to other fundamental concepts in reservoir engineering. In particular, we introduced Darcy's law and the very important concept of permeability, the flow capacity of fluids and reservoirs, in the following Part 3.